Hello and welcome everybody. Thanks for joining the ODTN session this afternoon. I look forward in you learning about the Open Disaggregated Transport Network project that we at ONF are doing. And I hope this proves interesting, and you got a taste of it this morning. And so I'm just going to start the session with my own talk about a general overview of the project and some details about what we're doing exactly inside the software and the integration with the devices. And then we have a great set of speakers that are going to take you through some of the different topics and different solutions that are part of ODTN. So I'm going to talk about the clear ask that we got from the operators, that we use ONOS as a platform. Why do we use it? I'm going to go through the different incremental steps that ODTN is taking. A few mentions about the trials that we're doing, next steps, and a few takeaways. So we got a clear ask from the operators, especially two, which are really strongly collaborating with us, and I thank also in this audience, which are NTT and Telefonica. And they wanted, at least in this domain, a clear data center interconnect solution with open and standard APIs, a rapid cycle of innovations in terminal equipment, especially transponder, with a clear separation of behavior between the transponder and the open line system, a solution that enabled a set of services to be rapidly created, prototyped, and tested, and have a support for an OLS that could carry any given kind of signal, alien wavelengths, and a modular and production-ready platform with a CI/CD pipeline for a DevOps environment. So this was a clear ask that we got from many operators, especially NTT and Telefonica, which are partners of the ONF, but also Telecom Italia and others that are really working with us on this. So as a platform, we picked ONOS as a SDN controller because we already had a modular architecture with support of multiple southbound protocols, which is something that was very important for us. It was already having support for multiple device models, so we're capable of accepting different variances of the same model, for example, OpenConfig with different variations depending on the device, and it's easily extensible. If you've seen the ODTN demo at the booth, we wrote a driver for CASSINI in like less than a week. So that's how easy it is for you to integrate even your own device in here. ONOS provides resiliency in case of failures, due to multi-instancy and device mastership handling, not only in OpenFlow, but also through netconf, by internally picking who is the master and establishing the proper channel to the device. We have an initial dynamic configuration subsystem, which has its pros and cons. We're trying to address the cons, and I'm going to talk a little bit more about it later. We have a good performance. I mean, you've heard it from Comcast this morning. They put it in trial. They're looking at putting it in real production, so it's pretty good. It's production ready, it's proven code, so that's why we picked ONOS. I really want to touch up a little bit on the southbound protocols that we are using for ODTN. Especially we're using netconf and YANG, with the YANG tools and the dynamic configuration subsystem on that side. We use REST and RESTconf both at the northbound and at the southbound. And the northbound for the TAPI interface, at the southbound to talk to the OLS subsystem. But we're also looking at possibly leveraging some newer interfaces, gRPC and GNMI. So we currently support existing deployments that expose netconf interfaces, but we're also looking ahead with possible transponders that are already in the market from some vendors that support gRPC-based interfaces. But the common point here is that all the transponders support OpenConfig, and I will go over it later. So a key component in ONOS is this concept of a driver, which is a device-specific element. Think about it as you have a printer in your home, and your computer needs a driver for that printer. This is the same concept. You have a device in your network, you need a driver for that device in order for ONOS to translate high-level concepts to low-level device-centric calls. It's on-demand activated, so if you have only, let's say, Nokia in your network, you just activate the Nokia driver. If you have plenty, they can coexist at the same time in ONOS. the real point is that you can integrate also different Yang models, and it doesn't change the ONOS core nor the ONOS Northbound API. So on the Northbound of ODTN, it's always TAPI. That's not going to change because some devices is going to be different from what we have tested. And this is also what rapidly enables us to prototype new devices and test new things. So a little bit of a touch up on what we currently have on the dynamic configuration subsystem, which we use especially on the Northbound for bringing in the TAPI models. So Transport API from ONF, which Karthik is going to talk a little bit more about later. We have a store where we save some of the device configuration, and then an initial implementation of a Southbound where we automatically generate the XML. That still needs improvement, I'm not going to lie about it. It still needs a ton of work also to make it production ready, but thanks to the requirements that are coming in from NTT and Telefonica, we're also addressing key components of this architect that need to be made production ready. So we as the ODTN project, and in particular inside ONF, we thought that an incremental approach would be the best choice for the ODTN project, because if you pick too broad of a target, you're never going to get it done. So instead, what we said was really start with one simple step, choose the common APIs for that use case, for that step, do the implementation, test it, and iterate over it. And then, when a good chunk of that implementation is there and it's tested, go to the next phase. So that's what I'm going to present to you today, the different phases that ODTN is covering. So each phase builds on top of the previous one and brings in further enhancements, further devices, further implementation. So a very, very, very high level design that the ODTN solution brings in is that in the Northbound you have TAPI over RESTconf exposed to the Northbound interface of ONOS, which talks to the ODTN application. That makes the translation between high-level TAPI concepts and internal ONOS representation of those concepts. And it really understands the semantics of the request that's coming in from an OSS BSS of the operator. Then you have an ONOS store, which saves the configuration, saves the information you've been asking for, and manages the resources and generates device control and configuration through many different protocols, for example, NetConf, GNMI. And then you have those drivers subsystem that I've talked to you about that really abstracts the nuances of each specific device, and maybe they support a version of OpenConfig which is 2.0, while other device supports a version of OpenConfig which is 2.0.1, while that abstraction is kept in the driver subsystem. And then you have OpenConfig as a model talking to the devices over NetConf, or TAPI over RESTconf for the OLS, for example. So let me go to phase 1.0, which, spoiler, is done already. It's what we are currently demoing at the booth. So the use case is a point-to-point connection made of 2 transponders and an optional open line system in the middle. If you decide to put the open line system in the middle, that open line system has to be configured out of band, because ONOS at the moment is in the works to support the configuration of the open line system, and that's phase 1.5. The phase 1.0 enables a cross connection between a line side and a client side port of the transponder, each transponder in the network, in order for the traffic to flow from the client side, which is connected to your data center, to the other client side, which is the other data center, the other end of your point-to-point connection. The APIs that we chose are the Transport API for the Northbound through RESTconf, and OpenConfig models over NetConf to the Southbound. So why did we choose OpenConfig? This is a good question, and I wanted to clearly address that point. It's a well-known API, and you've heard about it in multiple contexts, not just ODTN, Stratum, next generation ONOS. It's a well-known set of models that exposes device capabilities. It has a specific set of capabilities for the optical devices, so that's why we chose it. It's already supported by many vendors. I can name a few. We have already integrated Nokia hardware, we have already integrated Infinera hardware, NEC hardware, CASSINI with IP Infusion, and I know that other companies such as Siena have an OpenConfig Northbound, and I plan to do work with them on that. It's a proper abstraction for the transponder device capabilities and information, both at the optical layer and in general device information. And also defines the capabilities at the correct level for programmability, but also abstraction. It doesn't go too deep with information that I don't really care about from a controller perspective. It supports also vendor-specific features that are easily to extend in the Yang model and easily to bring in ONOS itself. And extensible and open source. It can represent both multi-layer with and without the OTN parameters. Then, moving to the northbound of ONOS, why TAPI? Again, well-known API, many interoperability testing that prove that it's being tested and deployed on top of many OLS and optical domain controllers in the industry. It has a proper abstraction for a high-level optical domain programming, and Karthik is going to talk more about it later. And it can represent both multi-layer and end-to-end provisioning. And it's a great community of vendors and service providers coming together to define this set of APIs. And we as ODTN are engaging with them to bring in our use case, but they're also engaging with us, telling us this is what you can do with TAPI, and this is some capabilities that we can expose to it through it. So this is the topology we're looking at, ONOS as a controller, the two transponders. One point that I want to make is that the transponders are bookended. So Nokia transponders are going to talk to Nokia transponders. Infinera transponders are going to talk to Infinera transponders. At the moment, we're not taking into account the possibility of a Nokia transponder talking to an Infinera transponder, because that brings in a whole new set of problems and requirements that we're not ready to take on. So maybe in the future. For phase 1.0, the OLS is configured out of band. We work with the Infinera XT300, the Nokia, that model, and NEC and CASSINI. And the open line system really carries alien wavelengths across the two transponders. The implementation that we have done, we've auto-generated the RESTconf Northbound interface based on the TAPI models through the dynamic configuration subsystem. We've implemented the ODTN service application for an end-to-end control through the TAPI model. We implemented the OpenConfig ONOS driver supporting a standard version of OpenConfig, and then specific drivers were developed where there was a need for the changes inside the model for a device-specific implementation, such as the Infinera device. Oh, this was animated once, whatever. So what happens, and the first thing that you have to do is discover the topology, okay? So how do you discover the transponder? The first thing that happens is that you configure the OLS completely out of bound. Then the OSS BSS of the operator sends an endpoint to ONOS with the transponder interfaces, and IP and port. ONOS does the reach out, that's point 3 and 4, does the reach out to request the topology information, such as the ports, such as the device info, to that transponder. At that point, ONOS exposes this topology information through TAPI as northbound through service interface points. So the client side and the line side are exposed as service interface points through the TAPI northbound, and ONOS stores the transponder and device information inside the ONOS core, so it's replicated and it's kept for future use. And all of this discovery is done through OpenConfig. So we basically issue first a hello message through netconf, then we ask for capabilities of the device, and then we ask for its ports, and that is all done through XML exchange messages over netconf. So this is transponder discovery. So then, when you have discovered the topology, you need to provision things. So what happens is that the OSS BSS of an operator sends a TAPI connectivity request to ONOS with the two service interface points that are the client side of the end-to-end connection. So in this case, service interface point number 1 and service interface point number 4, which are at the end of the point-to-point connection you want to make. Then ONOS computes an OpenConfig payload to create a cross-connection per transponder to make the client-side port connect to the line-side port that goes down to the optical fiber. and sends it down. In particular, what we're doing is we're doing a logical channel assignment in OpenConfig. Then the transponder makes that cross connection inside itself, enabling traffic from the client side to go to the line side and vice versa. And ONOS stores this configuration of the transponders and can return it to anybody who's asking through TAPI. So that connectivity request is satisfied, and then is stored inside ONOS to make sure that if the OSS BSS requires it, we have that information for him to have. So the interesting thing that I want to point out here is that on the left side you see a TAPI connection endpoint, the two connection endpoint for the request that we are making, and that gets translated to the logical channel in OpenConfig. So this is what is the translation between the TAPI concept and the OpenConfig logical channel to enable that cross connection. And on the right side is what we're sending down to the device. This is instead of on the northbound and internally to ONOS, how we keep the information from the request of the OSS BSS. So just as something that we have done in the past few weeks, and I want to talk about, and we have a demo of it, we have also integrated the first white box transponder with CASSINI, thanks to EdgeCore that makes the device, and IP Infusion, who makes a little bit of the ONOS software in there. But what I really want to point out here is that we're also using Telecom Infra Project specification, which is TIE. So some of you might be familiar with SAI, which is the switch abstraction interface. Here we have TIE, which is the transponder abstraction interface, and it's a common API to talk to the optical line side module. So at the moment in the demo we have here, we have ACO line card from NTT Electronics, but with the same API, bringing in a library for a vendor in the device, there is a possibility to put in, for example, Acacia, Aclaro, DCO, ACO cards, depending on your need. But that is completely abstracted through OpenConfig. So you can more plug and play depending on your needs. And that is integrated as yet another transponder controlled by ONOS. Okay, so this has been done. We have done this integration. We are capable of controlling the transponders through OpenConfig. So what is the next step? The next step is, if you remember the first slide, we're controlling the OLS out of band. You need to still go in the CLI and provision the end-to-end wavelength across that OLS and those amplifiers and WSS and max ponders. So instead, we say, okay, for next phase, we take that control back to ONOS, and we want to do that. So still a point-to-point connection, two transponders, at least two, and an open line system. But this time, it's an end-to-end path provisioning, both the transponder and the OLS. Same northbound API, TAPI, same southbound API towards the transponder, OpenConfig, we're building on phase one. But we're using Transport API 2.1 over REST for the OLS. So we're asking the OLS vendors, which I will talk about later, to implement that Transport API. And some of them already have maybe an older version of the Transport API that they are exposing. We're asking for 2.1 because it exposes a lot of optical parameters, and Karthik is going to talk more about it later, through the photonic media, and we need those parameters to properly tune the end-to-end path. So topology discovery is the exact same as phase 1.0, but we're also giving it the information about the OLS. At the moment, for the OLS vendors, we're working with ADVA, which is much along the implementation of their TAPI 2.1 interface on the northbound, but also Corient and Infinera. We are working with Nokia also on the OLS side, and also in talks with Juniper. These are at different stage of implementation of the TAPI northbound, but that is the request. So we're standardizing also the interface towards the OLS. So what is the implementation? We have done the augmentation of the transponder drivers to properly tune the wavelength for properly talking to the OLS. We extended TAPI Northbound on ONOS on 2.1, and we have started the driver implementation for a TAPI-based OLS through the discovery of ports and device information on the southbound. What's in progress, and that's why phase 1.5 is not yet completed, but we're working on it, is that we have a connectivity request for the OLS in the TAPI, that's in the southbound, that still needs to be done. We still need to target power configuration and negotiation between the OLS and the transponders. That's a component that we still need to do. And we also plan to have other OLS integration, so that's ongoing work. So how do we discover the OLS? Same as the transponders. The OSS BSS sends a JSON file with the IP and the port. It gets sent to ONOS, and then ONOS tries to establish connectivity by asking the TAPI topology to the OLS through a REST call on TAPI. And the OLS is going to return a big switch abstraction with many service interface points that are the network-to-network interfaces that he's exposing towards the transponders. At this point, ONOS stores all that information in its distributed store, and this appears as a device in ONOS and in the ONOS topology. And then we can actually properly configure it. So what we do is that we create an optical connectivity intent, identifying the two service interface points that we need to which the transponders are connected to, let's say SIP1 and SIP4. We can optionally request the wavelength configuration to the OLS or enforce the wavelength configuration to the OLS, depending on the OLS implementation. Then after the negotiation of the wavelength, we do a TAPI connectivity request to the OLS with or without the wavelength. And that asks the OLS to establish a path going across its multiple underlying devices, so the max ponder, WSS, the amplifier, and all of those, from SIP1 to SIP4. The OLS does that, sets it up properly, and returns an OK message to ONOS. And at that point, ONOS will then engage phase 1.0, provisioning the transponders. So really the end-to-end provisioning goes in these steps. The operator OSS BSS first requires an optical layer provisioning through TAPI. That goes in there, creates an ONOS connectivity, optical connectivity intent, provisions the OLS, then provisions the line side of the transponders to properly tune the wavelength. Then the OSS BSS requests an end-to-end layer 3 connectivity, and ONOS configures the cross connection in the transponder, that's phase 1.0, and then the end-to-end path is properly provisioned. So this is a high-level overview of what's happening for the end-to-end connection to actually be there, and the traffic to really start flowing. So, okay, it's great software, great implementation, great slides. Are you actually testing this? Yes, we are. So thanks to the effort both in Telefonica labs and NTT Telecommunication labs, we are testing everything that I've talked about in the different phases with different set of equipment, especially in Telefonica, Nokia transponders, and Dominique and Kwan are going to talk more about them later, and an open line system with ADVA. In NTT Telecommunications, we have Infinera transponders, or IP Infusion plus EdgeCore with the CASSINI box. The open line system is still to be defined, and they're also in the process of testing different things. So a little touch up on phase 2.0. I don't want to take too much of your time, but going forward, we also want to look at something which has a mesh ROADM network, right? At the moment, it's a point-to-point connection. We also want to look maybe at a ROADM ring with N transponders. With ONOS provisioning both the transponders and the ROADMs. The ROADM API is still yet to be decided. Obviously, Open ROADM is definitely a candidate, but it's not the only one. And this is really depending on the operator's ask. So if the operators will come up with some certain API for the ROADMs, we're going to implement that. If it's Open ROADM, clearly that could be a possibility. If it's TAPI, that could be another option. So will be kind of the overview of a possible ROADM-based topology with multiple transponders and multiple ROADMs, all controlled by ONOS. Note, OpenConfig is still there for the transponders, TAP is still there for the ONOS provisioning. So we're not going to change those. So let me talk about the next steps. We are here, and by March 2019, it's a pretty big commitment. We're going to complete the OLS integration. And we're going to have a demo of phase 1.5 with the OLS integration at OFC. Hopefully that's get accepted. I submitted a paper to do that. And we're going to start at the end of March. We're going to start some lab trials of phase 1.5 with a complete OLS provisioning. And then we have a multi-vendor transponder and OLS trial. We're going to obviously harden the platform and start the definition for scope and API for phase 2.0. So since I have 2 minutes left, let me go through the takeaways. What I really want you to take out of this session. So ONOS is ODTN is the first and at the moment kind of only end-to-end open software stack, fully open source, that goes both from the device to the controller to the API, both at the southbound and the northbound. Those APIs are TAPI as a standard for the northbound and the OLS, and OpenConfig for the transponders. ODTN leverages the architecture, performance, and scalability of ONOS, and while it integrates a wide variety of vendors for network equipment. It has an incremental approach and has lab trials with a feedback loop that brings in the more incremental requirements and augmentations to the platform and the code. I want to thank all the community that has been working with us as ONF inside the ODTN project. I want to thank especially NTT and Telefonica for driving the project as operators, for clearly expliciting their asks in the reference design, but also all the vendors and the software and the system integrators that brought in their expertise and their devices and their APIs for us to make it a successful project. So, useful info, there's a wiki. You can check out all the demos we have done, all the tests, all the technology that we are using. More information is going to be there. If you want to join, we have a technical weekly meeting every Tuesday at 8 a.m. Pacific Standard Time. It's open, it's free to join. Just bring in your expertise and let us know what you think of the project. And there we really talk about technical details. Do we model this port in this way or the other way? How do we implement this in ONOS? Do we need to do this augmentation to the TAPI model? All of these things we talk about in the Tuesday call. And if you have any questions, that's my email. Or I can also take them now. I know it was a lot of content, so it's a lot of content, and maybe it's hard to take it on immediately, but the slides are going to be shared and the talk is going to be recorded, so feel free to look it up later. But if you have any questions, I'm happy to pass a microphone to you, and so you can ask them. Please.
Yeah, we will talk about the white box for the optical transportation network. We see some white box on the transponder side from like a Warrior or CASSINI, right? But I have not seen any kind of a white box for the OpenLAN system yet. So as you listed, also vendors in this list is almost come from the OEMs. So my question is, do you see what is the issue, for the ODMs to jump in for the OpenLAN system? And what will your view when that's going to happen for the white box?
Okay, so that's a very good question. There's a couple of sides to that, in my opinion. So one side is that an OpenLAN system has a lifespan of a lot longer time than transponders and other type of devices in optical networks. And also there is a lot of expertise being put in there by vendors. So it's not as simple as creating a box, which is what a lot of white box vendors are doing, but there's a lot of expertise being put also in the software. So definitely full white box OLS is something that I would like, a fully disaggregated solution where I can talk and discover and configure multiple type of equipment from many different vendors, not as a one component as an OLS, but really talk to the amplifier, to the transponder, to the muxponder. This is something that I would like. Do I see it happening down the line? Not really at the moment, so it's gonna take some time for that to happen. And it's also pending on the operator's request. So the OLS is definitely an investment in terms of money, because it's still quite some components to do so. And also the expertise to set up that connection between those two components is something that still has to be provisioned in open source, still has to be there in open source. So I think we're talking about in the terms of not months. So it's going to be a little bit a longer time frame for this to happen. Do I see it happening? Yes, but it still has a longer time frame, and probably a couple of years to really have that fully disaggregated. And this partially disaggregated model actually fits perfectly inside the operator's request. So I think that can suit our needs in that use case, and we can start deploying like this. But then have maybe those white box amplifiers and stuff like that expose the same API, for example TAPI, for example OpenConfig. So we then integrate them in ONOS, but it's going to be down the line. Any other questions?
So there are multiple applications, right? So there's metro applications, there's long haul applications. So how do you validate reach in this case? Is there some sort of design tool you use as topologies get more complex?
So at the moment we are not validating reach. So it's not something that we have done at current time. I'm talking with TIP and the TIP community to possibly use GNPy and PSE, so with the physical simulation environment, and that set of tools to maybe integrate them with this platform. Initially, that's an offline tool where you punch in the parameters and you get an output, if it's capable or not, and what is the best solution in there. But if all goes well and we have resources and commitment to do so, we can take that software online, meaning putting it on the Northbound of ONOS through TAPI or some other API, and really do that live. So we're making sure that we are meeting the reach, we're meeting the SLAs, and we're meeting the best capability of the optical network that we have.